All right. So we started last time. I don't know why it's not displaying just me, but okay, well, whatever. Anyway, so we finished last time talking about this example. So I'm just gonna quickly sketch up what that example looked like, so then we can proceed with it. So we had a we were looking at the electric. Oh boy, I need a thinner pen. Oh, still thinner. Is this one thinner? That's blue. How about this one? Oh, sorry. Pencil.
You can click it on it a second time and then.
Oh, nifty. Yeah, I don't usually use OneNote, like the new OneNote, so it's a little bit thin, but it'll have to do. Right, so we were looking at the electric field from a line of charge that was uniformly distributed. Actually, I do want it to be a little bit thicker. A line of charge that was uniformly distributed, and we wanted to find the electric field at some point a distance r away from the center, and the line of charge is length L, and we just set up a coordinate system that put y equals 0 at the middle, and then y runs up, and x runs to the right. Right. So that's the setup that we have, and so we already know that because this this particular setup has a uniform distribution of charge. Oh, I can't write on lines on this. That implies automatically that any given chunk of length L something about this is off. I don't know what it is, but whatever. Any given chunk of length L has charge Q, which is just equal to lambda times L, where lambda is just some constant proportionality. And so that is, if you double the length, you double the charge. And so we found that Q, the total charge, which we were given, that should be equal to lambda times capital L, the total length. And so in particular, that tells us that the constant of proportionality, this linear, or this linear charge density, is just Q over L, because we are given both those values. Similarly, we can find the charge of an infinitesimally thin piece of rod. That's just given by lambda dl. Now, in the coordinates that we're working in, so imagine that this is our infinitesimally thin rod, right? Or our infinitesimally thin chunk of rod. If this is dl, well, we can actually ask how far do you have to go in each of the coordinate directions in order to have a thickness dl. So in this coordinate system, dl is just dy, i.e. if you go y, so capital Q is usually reserved for the total charge of something. Lowercase q is usually reserved for the charge of a subset of a thing, or just some particular charge. No, so capital Q is just total charge. Lowercase q is not the test charge, it's just some amount of charge. Q is just a charge, capital Q is just always reserved for total charge. So in this case, dl, if you want a segment of length dl, you just have to go up in the y direction in infinitesimally small distance, dy. So we can actually write dq in this case as lambda dy. Okay, great. Now we're not done yet, obviously. So I'm just going to make a quick note here. We were trying to find the electric field, and the electric field is a vector. And so in this case, because I'm suppressing the z-axis into and out of the page, we just have that the electric field is the x component of the electric field in the I direction, plus the y component of the electric field in the j direction. And you would also have a z direction, but for our purposes, we're not worried about that. Also keep in mind that this system is cylindrically symmetric. So it doesn't actually matter, like the x and z directions are kind of interchangeable here. Like you could rotate the whole system and it wouldn't change anything. Right, okay. So we want the electric field at this point which is at location capital R, 0, right? Capital R in the x direction, 0 in the y direction. And the charge, this is located at position, say 0, y. So we want to know what the electric field is, the infinitesimal electric field from a point at 0, y at a point R0, meaning we want to know what the value of the electric field is at R0 when its source is located at 0, y. All right, so the point that I made last lecture was that because this slice of the rod is infinitesimally small, we can just treat it like a point charge, and we know what the electric field is from a point charge. So this infinitesimally small chunk of electric field, we just write down the electric field for a point charge. It is K times dq divided by r squared in the r hat direction. And now I have to be careful. So I actually need to tell you what r and r hat are. So this chunk of rod has charge dq. We already know what that is. Let me put that arrow elsewhere. It's at 0, y. That lowercase r, that refers to this distance. This is the vector r, and it has distance r without the little arrow over it, and the, oh boy, I just turned off the screen on accident. Am I still here? Excellent, I'm still here. Sorry, I just accidentally turned off the screen. And the unit vector r hat is the vector that points in that direction. So this is just a reminder. Recall dq is lambda dy, and lambda is just q over L. So this is q over L dy. Okay, now we have to do some geometry here. Like, we have some geometry to do, so let's do this. So this distance here is y. The bottom leg of the triangle is capital R. So we can find the length of the hypotenuse. The length of the hypotenuse is the square root of y squared plus r squared. And the unit vector r hat, if this angle here is theta, the unit vector r hat is the vector that has cosine of theta in the I direction, because it points to the right. It points to the right, and it's downwards with magnitude sine theta. Basically, this is the vector that looks like this, and it has the unit length 1, right? So you can figure out the horizontal component is cosine theta, the vertical component is minus sine theta. And then we can do a little bit more geometry. So we already, we already know what r is. So r is square root of y squared plus big R squared. We're just trying to rewrite all of these things in terms of quantities that we know, or in terms of the variable y. Now, cosine of theta is just big R divided by the magnitude of little r, right? Just from the triangle. So this is r divided by the square root of y squared plus r squared in the I hat direction. And then the sine theta is similar. It's y divided by the square root of y squared plus r squared in the j hat direction. Okay, so that means that we can combine all of these things to figure out what dE is. dE, is k times q times r over L times dy, and this will all make sense in a minute, r squared plus y squared to the 3/2 in the I hat direction, minus kq over L times y dy divided by r squared plus y squared to the 3/2 in the j direction. So all I've done is I've combined all of these facts. I took r, I squared it, because that's in the denominator. Then I multiplied that whole thing by this, and I combined like terms, moved things around, and so on. And then dq I rewrote as q over L dy. So if you look at this first term, you'll see there's a k, there's a q over L that comes from the lambda. There's an r divided by the square root of r squared plus y squared. That comes from the cosine theta. There's a 1 over r squared plus, or big R squared plus y squared. That comes from the lowercase r squared here. And then there's a dy, which comes from the dq. So all I've done is I've combined all of these terms into just something that's only in terms of either A, our coordinates, this is y and it's infinitesimal, or B, constants that we know, capital R, Q, L, K. So now the only thing to do, so the 3/2 came from, so R is y squared plus r squared to the 1/2. And then there's 2 of those from the 1 over r squared. And then there's 1 more from the denominator of the angles. So it's 1/2 times 2 plus 1/2. Right, so now all that's left to do is to just add up the contribution of all of these electric fields for the entire rod. So the total electric field is an integral of over the line of dE. Right, that's kind of a sensible thing to do, right? And so now we actually just need to convert this using our coordinate system. So this is equal to an integral from minus L over 2 to L over 2, because our coordinate that we're going to integrate is the y direction from minus L over 2 to L over 2. And then we have the following. Let me actually simplify this a little bit more. We have qk over L. And then just want to make sure I have everything right. We have dy over square root, not square root, over r squared plus y squared to the 3/2 times r in the I hat direction minus y in the j hat direction. So all I've done is I've factored out the like terms. There's a y here, there's an r here, that's the I hat, that's the j hat, and then everything else is the same for both terms. So I factored it out and just made it a little bit more straightforward, a little bit simpler. Now, in principle, you might think that this is like a hard integral to do. Maybe you've never seen an integral with unit vectors in it. But it's really not once you realize that you can just split integrals that are added together. So this is really QKR, or let me write it in proper order. It's KQR over L, integral from minus L over 2 to L over 2, times dy over r squared plus y squared to the 3/2 in the I hat direction. So that's the first term, right? I pulled out an r and so on, minus kq over L times the integral of minus L over 2 to L over 2 times y dy over r squared plus y squared to the 3/2 in the j hat direction. Right, yeah, r hat became cosine of theta minus sine of theta, or cosine theta I minus sine theta j, using just by looking at the geometry of the setup, and then we rewrote that in terms of r and y. So now these are just integrals that we can do. Capital R is just a constant, and these are now like they're a bit messy integrals, but you can do them. So the x component of the electric field, that would just be this thing. We can do this integral. And so I challenge you to do it yourself. It works out that you get KQR over L times y over r squared times square root of r squared plus y squared, evaluated from minus L over 2 to L over 2. And this works out to be KQ over R times the square root of r squared plus L over 2 quantity squared. Just is what it is. The j is negative because the unit vector points downwards, right? Like it's pointing that way. That's all. That's just because the unit vector, or the vector started out above the y-axis, so it has to point down. So that is the x component. You can do this integral. I'm not going to go over it. It's not a calculus class. And then if you do the y integral, you find that it's miraculously 0. So I'm actually going to spend a minute to explain why you might expect that. So let's take an aside to discuss something that you may have talked about in math class, and that's this is technically, it's just a math trick, but it's a discussion of even and odd functions. If you've never seen this before, it's a remarkably useful trick. So let's say that you're trying to integrate two separate functions. One function looks something like this. You have x and f of x here, and it looks something like this. And you want to integrate it from minus a to a, right? And then there's another function, maybe looks similar, or not similar, but something like that. And you want to also integrate this from minus a to a. Now, in principle, these are just terrible drawings, but the point I was trying to convey is that this function on the left is the same upside down and backwards as it is forward and upright, i.e. it has the property that f of minus x is equal to negative f of x. We call functions that satisfy this property, we call them odd functions. Similarly, on the right, we have a function that has the property that it's the same on the left as it is on the right, i.e. f of minus x is equal to f of x. And we call these functions even functions. The denominator, yeah, I can just show it there, hopefully. I'll just, yeah. So the point is that we can, if we want to do this integral, remember the integral is the area under the curve, right? So the integral from minus a to a of f of x dx for this function just has to be 0 because it's upside down, because the left side is the exact same as the right side, just upside down. So the positive area on the right cancels out the negative area on the left, and you're left with 0. Whereas if you were to do the same integral on the left side from minus a, that's a q, minus a to a of f of x dx, you would find that it's just twice the integral from 0 to a of f of x dx. And that's just because, again, the left side is the same as the right side. And so you can just double the right side and it'll give you the same answer. So this is a nifty property that you can use. And if you observe that a function has this property or this property, you can simplify integrals a lot. So how does this actually play a role in what we were just doing? Well, it turns out, why don't we take a look at the integrand for e of y. Let's copy this and bring it down. Copy, please. All right. Just trust me when I write this. So the integrand that we had was y dy, or the integral that we had, times r squared plus y squared to the 3/2, integrated from minus L over 2 to L over 2. Right, this is what we were working with before. So in this case, f of y is equal to y divided by r squared plus y squared to the 3/2. And so let's check. Indeed, f of minus y would be equal to negative y. All I'm doing is plugging in negative y in place for y, divided by r squared plus minus y squared to the 3/2. But that just simplifies to minus y over r squared plus y squared to the 3/2, which is just negative f of y. And so the integral that we were doing up here, when we had to do this integral, is an odd function, or we're integrating an odd function. And so we can just read off that the answer is 0 automatically without actually having to do any work. That's just a nifty math trick that we can do here. Now let's take just a minute and step back and think about the general steps that we used here to find the E field. So the general steps that we took, first, we identified a good coordinate system. In this case, it was really easy. It was just x and y. But we needed that coordinate system in order to be able to write that small segment of length in terms of some coordinate. Yeah, yeah, you could use that property on exams, yeah. Second step, we picked an infinitesimal amount of charge, or an infinitesimal chunk of charge. I actually really like how this is writing. And we computed the electric field from that chunk. So just as a reminder, we did that. Here, we wrote out what dE is in terms, this is just the infinitesimal electric field from just a single chunk of charge, right? And to do that, we had to do a lot of work, right? We had to figure out what dq was. That was the easy part. That was just q over L dy. We had to figure out what the distance was in terms of the variable y. We had to figure out what the unit vector was, r hat, and then we had to combine everything together. It's a bit of work, but there's no calculus there. Third step, we integrated. dE over whatever thing. In this case, it was a line. In general, it could be more complicated. Sometimes, some of the terms vanish for symmetry reasons, or some of the terms are simple. And when I say symmetry reasons, I mean things like the oddness property that I mentioned above. And then fourth, which is optional, express your results as a vector. So you would write, we didn't actually do this, but you would write something like E equals stuff times I plus stuff times J, or if that stuff was 0, it would just be stuff times I, right? So in this case, it's just that. And that would be your answer. That would be your final result, and then you'd be done. So we're going to use these steps again. We actually are going to do another example. This is a slightly more complicated example, but it's worth doing because you guys will need practice doing this. So let's do that. No, please never do that. It just looks awful. I hate it a lot. Like, it's technically not wrong, but you'll never see anybody outside of like a very intro class do that. Right, okay, so let's do another example. This time, we're going to find the electric field. By the way, the reason why we did that, why we did this electric field business, is because now, if we took an electric charge and put it at point P, we would automatically know the force, because all you have to do is multiply the charge by the force. If you don't know the tuple notation, don't worry about it, because you should never use it anyway. Right, so we want the electric field again, because the electric field's always useful. We want the electric field above a uniform disk, above a disk of uniform density, uniform charge density, rather. So we're going to work that out. Slightly more complicated, right? So here we're going to assume that we're given the radius of the disk is A, and the total charge is Q, capital Q, right? So those are just things that you would be told. And we want the field, say, Z units above the center of the disk. We want E at 0, 0, Z. So the picture here, you have a disk. This is all, by the way, once things start getting straight, or not straight, once things start getting curvy, my drawing gets significantly worse. We put a point here at 0, 0, Z above the center. This distance here is A, and there's a total charge Q on the disk. This is and we want to find the electric field at that point, at 0, 0, Z. Right, so step one, find a coordinate system, right? So here we have a different symmetry. In this case, we actually didn't really have to worry about what symmetry to use, what symmetry would give us coordinate systems. But here there's a fairly obvious symmetry that we should worry about. Cylindrical coordinates. We want the electric field. It's not really a full sentence for what it's worth. It's like a phrase. We just want the electric field at 0, 0, z. Right, so the correct choice, you can use any choice, but the best choice would be cylindrical coordinates, right? Because you have polar coordinates along the plane, and then you just have vertical, normal Cartesian coordinates. So that's cylindrical. Step 2 would say something like, what about the infinitesimal chunk of charge? Well, so we have to use the correct chunk that's associated with the coordinates we chose. So rather than just putting a square here, a square isn't compatible with the coordinate system that we chose. So instead, what we want to choose is we want to choose a chunk of charge that matches the coordinate systems. Like this. Where this distance here, we'll just call r, and the say the distance away from the axis, call that phi. So now we have to, and this small chunk of charge will have charge dq. How's that different from A? R doesn't go all the way to the boundary. A does. R is a variable here. R is telling us where the small chunk of charge is. A is just the radius of the disk. It's the actual radius. So I'm going to draw a quick picture just so you can get an idea as to what the area of this small chunk of charge is. So here we have a small chunk of charge. This distance, or that angle, that's d phi. What axis? What do you mean? What axis are we referring to? Sorry, this is like the y, like the x-axis, and this is the z-axis. Say. So that angle, that's a very small angle, phi. Here's our small chunk of charge, by the way. This width, the width of our little arc, is a width dr. It's a small extension away from the coordinate, where this distance here would be r. So then this arc length is r d phi, at least approximately. Actually, technically that's the bottom. But because we're working with infinitesimals, it doesn't matter. So the area of this small arc, you'd think that it would be something complicated, but really it's not. And the reason for that is because we're working infinitesimally, so this thing isn't really this curved. It's actually very nearly just a box because the angle is very nearly the same. I've just blown it up. So the area here, dA, is really just r times dr times d phi. So I just multiplied this with this, length times width. So that means that dq is just sigma dA, where sigma is our charge density. In this case, it's an area charge density or a surface charge density. And so we have that this dq is sigma times r dr d phi. Okay, so now we need to figure out what's sigma. Well, sigma, we can do the same thing that we did before. With the line charge, what we did to find lambda was we just, well, let me actually go into a little bit more depth. So in principle, we could just take the total charge and divide it by the total area because this is a uniform charge distribution. But I'm going to do a little bit more just to show you how this works technically. So, or how this works in more detail. So the total charge is just an integral of all of the little baby charges, right? So the total charge, move this over here, which is q, is just an integral of dq, right? It's just an integral over all of the little charges. But dq, this is over the disk. dq is sigma times r dr d theta. So this is an integral over a disk in terms of the polar coordinates r and phi. Sorry, r dr d phi. So we would have an integral from 0 to 2 pi, and an integral from 0 to a, because that's the size of the disk, of sigma times r dr d phi. It says disk, just written poorly. It's an integral over a disk, right? And so now we can just do this integral, and it works out that this is completely expected. This is sigma times pi a squared, because this sigma is a constant, so you can pull it out. And then you're just integrating the area of a disk, and the area of a disk is pi a squared. So that tells us that sigma is just q divided by pi a squared. Easy peasy. I'm going to put a box around that so you remember it for later. All right, so that means that dq is q over pi a squared times r dr d phi. So far, so good. Remember, we had to get dq before. It's just a little bit more complicated now. So what about dE? The small chunk of electric field that we get from that amount of charge, i.e. the electric field from that charge would point something like that. How much is it? What direction does it point in? So dE, the starting formula is the same. It's just k times dq divided by r squared, and I'm going to tell you what these things mean in a minute. So here I've defined the vector that points from our small chunk of charge as capital R. So when I divide by capital R squared, that's dividing by the magnitude of this vector that points from somewhere on the disk to the point of interest. And then the unit vector r hat is just the unit vector that points in that direction. So again, we use geometry to find out to rewrite what those vectors are. So the length of that vector, well, we use the Pythagorean theorem. It's r squared on one base and z squared, or r on one base and z on the other base. So r is just the square root of little r squared plus z squared. Here z is treated as a constant, right? It's just the position that we're interested in. Now, finding r hat is hard, or it's harder. So, and the reason why it's harder is because depending on where you are, it's pointing in different directions and it's rotating about. So you would have to have all three coordinates. But we can actually use is r in the center of the slice of is dq in the center of the slice of area on q? It doesn't matter because it's infinitesimally small. Yeah, so the center is where the object is, because imagine it's like teensy tiny. So what I was saying is that it would be hard to figure out what all of the components are for the r hat vector, because it's pointing every which way. But consider this. For every dq that you have on one side, you have a mirror dq on the other side that has the same magnitude and same direction, except it points in the opposite way. So the net result of adding up all of those components of dE would be that the only direction that doesn't get canceled out is the z direction, because if there's a dq on one side, the x direction component that you would have from the electric field would be canceled out by the x component direction of another chunk on the opposite side. This is a symmetry argument that I'm making. This could all be done with symbols, but we don't have to because we're doing physics. We don't have to, we can use our brains here. So, and by the way, this is the exact same argument that you make for an odd function. Basically, if you were to integrate this thing, or if you were to plot this thing as a function of phi, it would be odd about the line that where phi is equal to pi, basically reflecting about the vertical axis where phi is equal to pi. Like if you take phi as pi over 4, then you take the one on the other side, which would be phi plus pi over 4. Then they'll be equal in magnitude and opposite in sign. Just to give a simpler picture. You have a chunk here and a chunk here, and we're interested directly above. So the electric field from one would be here. The electric field from the other would be here, same magnitude, but just pointing in the opposite x and y directions. So phi between the z and x axis, or phi is the angle along, like, around the disk. It's between x and r. So like from above, it would look like x here, and then our chunk is like here, and this angle here is phi. If that helps. And so when you add those two vectors together, you just stack them on top, you end up with a vector that only points in the z direction. And so the whole point here is that the y component of the vector and the z components, and the x components of the vector will cancel with other chunks of charge. So we only have to worry about the z direction. That's the trick. And that's what makes this problem doable, and so it makes it a lot easier. So we only want short version of a long story is we only need dE in the z direction, because all the other components are going to be 0 anyway once we add everything up. So that means we only need the z component of r. Yes, r is harder. And so that's doable. The z component of the r unit vector, that would just be effectively the cosine it would be the cosine of this angle, right? And the cosine of that angle is just z over capital R. So the r component of the z, or of the, sorry, the z component of the r unit vector is just z divided by r. And so we know what capital R is now. Capital R is square root little r squared plus z squared. So this makes it just a lot easier. So now we can combine everything. dE in the z direction, I think there's a typo in my notes, it says the x direction, is, well, so first there's a k, there's always a k. So this is dq. We can pull out that q, so we can pull out a q over pi a squared. So I'm going to put a kq here. Z is going to show up because we want to multiply it. We want to multiply it by r hat in the z direction. So I'm going to put a z up top, and then I'm going to divide by the pi a squared. So it's q over pi a squared times k, and I'm going to get rid of these circles at the end. And then it's times r dr d phi, that is our area component, divided by r squared plus z squared to the 3 halves again. And this z pairs up with the denominator to give you r hat in the z direction divided by r squared, and then the q over pi a squared pairs up with the numerator to give you dq. It's unreadable, so that's why I'm erasing it now. Right, so the point is I just took everything. I took dq, I plugged that in there. I took r, I plugged that in there, and then I took the z component of r and plugged it in, and just mashed everything together, and this is what you're left with. And remember, we only need the z component because all of the other components cancel. So that's why we're not even bothering to calculate them. So step 3 then says integrate. So now we just do an integral. So the electric field in the z direction is just an integral of each part of the electric field in the z direction, integrating over the disk. No, so this is a component, so it doesn't have the hat. This is the component of a vector. It doesn't have the arrow, it doesn't have the k hat. And so we can now just do this integral. This would be kqz over pi a squared, integral from 0 to 2 pi, integral from 0 to a. RZ, so RZ is the Z component of the vector that points from our small chunk of charge to our point of interest. It's the Z component of the unit vector. And so then we would have an R dr d phi up top divided by R squared plus Z squared to the 3/2. What arrow I drew? Oh, sorry. Yes, it's pointing to R hat. That's all. That is the Z component of that vector. So now you can go home and do this integral. It's not a particularly tricky integral to do. It's just a simple substitution, but I'm not going to do it. No, we actually won't do a whole lot of volume. But the end result is you get 2kqz divided by a squared times 1 over z minus 1 over square root a squared plus z squared. And that's the answer. That is the electric field in the z direction. And we also know from the argument that I made above that the electric field in the x and y directions are 0. And so the end result, the final result, step 4, is the electric field at the point 0, 0, z is equal to 2kq over, I'm missing a pi. Sorry. I'll have to fix that in my lecture notes too that I upload. Pi a squared? No, sorry, the pi goes away. Pi goes away because I do the phi integral as well. So it's 2kq over a squared times 1 minus, sorry, 1 minus z divided by square root a squared plus z squared. And this points in the k hat direction. And that is the electric field at that point. It just is. Like, so now if you wanted to figure out, so all I did was like, so dE in the z direction is just the z component of this vector, right? So I took the z component of r that we calculated as z divided by the square root of r squared plus z squared, multiplied that together, added that in. We knew what dq was, so you can plug that in there. Pi disappeared because part of the integral, right? One of the integrals is an integral from 0 to 2 pi. And then the r squared is just the square of square root of r squared plus z squared. R hat is z over r because trig reasons, basically. Will our problems in homework and exam be general, or will we be given values for the parameters? I'm not writing the exams. I am writing the homework, so it'll probably be general. Could we have just deduced that EY and EX are 0 since the point is 0, 0, 0, meaning there's symmetry since there's a disk? Yeah, that's the argument that I made. Because of the symmetry of the disk, those points have to be 0. I was just explaining why that symmetry means that it's 0 instead of something else. That's all. All right. By the way, this example is done in a lot of detail in section 1.3. So if you want more detail, go take a look there. I know I kind of went quickly, but we only have half an hour left, and I still have a bunch of notes to go over. A bunch of stuff, rather. So unfortunately, I've explained that a whole bunch, so I'm just going to skip it, but stick around after lecture and I can explain again. Right, so we can use what we just talked about, the infinite, or a line or a disk, to discuss infinite lines of charge. Infinite lines and planes of charge. So rather than just a finite line segment, it's just an infinitely long line. Or instead of just a finite disk, it's an infinitely large plane. We can now use what we just learned to discuss that. So the question is how? And the trick is notice that both of our answers, here, our answer for the electric field for a line, was just, let me find the answer. It was just kq over, well, it's just this thing. And it depended on this length L. And similarly, our answer for the disk depended on the radius of the disk A. So if we just take the limit where L and A go to infinity, that should get us most of the way, right? Because that just means it's a line that's infinitely long, or a disk that's infinitely large in radius, which is an infinite plane. There's just a little bit of work that we have to do, and that's that if the length, or if the radius go to infinity, that means that so does the total charge, because the charge density is constant. And so we would be stuck with infinity over infinity. So instead, what we want to do is we want to rewrite all of the capital Q's that we see in terms of the charge density. It'll be a more useful construct because an infinite line of charge is going to have an infinite amount of charge, right? So you'll want to, so it's not like somebody could say this line has an infinite amount of charge. You would want them to say this line has 5 units of charge per meter. You would want them to give you a density rather than just the total charge. So let's rewrite our answers in terms of lambda and sigma. So we already know how lambda and sigma relate to the total charge and the various dimensions like the length or the radius. So I'm just going to do that, and I'm going to tell you what the electric field from a finite line is in terms of lambda and its length rather than its total charge and its length. So in this case, it's k lambda L over r times square root r squared plus L over 2 squared in the r hat direction. By the way, something I didn't mention when we were talking about the line is that the line is actually spherically or cylindrically symmetric, right? So it didn't matter that this was the x-axis. It could have been the z-axis just as well. So this point is actually a whole set of points all the way around the line that will tell you the electric field, and it just points outwards, right? It just points in that direction. So that's why I'm writing the electric field in the direction of r hat. R hat points radially outwards from the line. Similarly, we can do the same thing with the disk, for the electric field for a disk. Now, this is a function of z. It's not a function of distance from the line. It's a function of distance above the circle, above the disk. And rewriting this in terms of sigma rather than q, we get that it is, let me make sure that I get this right. It's 2 pi k sigma times 1 minus z over square root a squared plus z squared in the k hat direction. So that just points straight up, right? And it like there is no symmetry there, so we don't have to worry about some sort of r hat. Okay, so now we can just freely take the limit. Because sigma and lambda, they don't change as you take the limit. They just are what they are. They're the constant density. So we take the limit where L and A go to infinity. So the limit, as L goes to infinity of the electric field due to a line at some distance r away from that line, well, hopefully you guys can do this. It's not very hard. You have to use some L'Hopital because it's infinity over infinity, but it works out to be 2k lambda divided by capital R in the r hat direction. Similarly, for the disk, this is when a disk becomes an infinitely large plane. The electric field at a height above this plane is remarkably simple, 2 pi k sigma in the k hat direction. I'm going to put a box around that because these are really, really useful. Right, so what these say is that if you make the line or make the disk infinitely long or infinitely large, a lot of the specifics about how long the line is kind of drops out, and it simplifies the problem a lot. In particular, if you have an infinitely long line, it doesn't matter that you are, come on, scroll, will you? It doesn't matter that you are, like you don't need to specify that you're exactly halfway between the top half and the bottom half, because every point has an infinite number of charge above it and an infinite number of charge below it. So it works for every point. So if you wanted this, if you wanted to know the electric field here for an infinite line of charge, you would just plug in that distance r, and the electric field would point in the r hat direction. This would be for an infinite line of charge that extends in both directions. But it would also work here because that equally well has an infinite amount of charge above or below it. And you would plug in this value of r. Similarly, for a plane, an infinite plane that extends in all directions, if you're at some point above it, it doesn't matter where you are above it, because every point has an equal amount of charge in circles around it. So the point is these formulas apply for every single point in space. If you have an infinite line of charge or an infinite plane of charge, these formulas are not just special cases anymore. They don't only apply at like the midpoint. They apply everywhere, because the symmetry of infinity makes it so that you don't have to worry about, is there the same amount above and below? Is there the same amount to the left and right? Because there's an infinite amount above and below. There's an infinite amount to the left and right. Now, something interesting here for the disk in particular, which becomes the infinite plane, is that it actually doesn't depend on how far away you are from the plane at all, which is really strange, right? It would seem that like the further you are away from the plane, the more electric or the less electric field you should feel, right? But that's just not the case. And the reason for that is because basically the contributions from if you're very, very close to the plane, the contributions from the points close to you give you a lot of effect. But the contribution from the points further away from you gets small very quickly. So when they all add up, you get one value. And then if you're very, very far away from the plane, almost every point on the infinite plane gives you the same effect, because they're all far away from the plane, right? So like here, you have a whole bunch of points, but they get far away quickly. Whereas here, they're all about the same distance away. And so you have a whole bunch of different, you have two separate effects. One where the close points contribute a lot, but the far points don't. That would be this point that's close to the plane. And for the points that are far away from the plane, all of the points contribute about the same-ish. And at the end result is that you get the same electric field regardless of how far away you are. Another way to see this is that if you are sitting at that point, Nicholas, I can answer that question later. If you're sitting at this point, it actually is impossible to tell how far away you are just by looking around, because it's not like you can see the edge, and if the edge gets small, or if the size of the disk gets smaller, then you're further away. It'll always take up your entire field of view. So it's effectively impossible to figure out how far away you are. Anyway, you might ask why why we would care about this, because these don't exist in reality. But the trick is that they're like, everything in physics is just an approximation, right? So imagine that like you're an ant and you're crawling on a 2 square meter table, right? And maybe that 2 square meter table has some charge. Yeah, it's in section 1.3. If you're crawling in on that charged table that's really, really big compared to you, from your perspective, it's basically infinite. And so from your perspective, this would be a pretty good approximation, even if it's not 100% accurate. Similarly, if you're an ant crawling along like a tube that's really, really long compared to you, and it's charged, again, the electric field would basically be this, even though it's not 100% accurate, because the scale of what you're measuring is very, very small compared to the size of the object you're comparing to. And so just as an approximation, the line is infinitely long or the table is infinitely large is good. It does work for the case of the infinite line. That's precisely what I'm talking about. Oh, why this is an issue of dimensionality, and I can go into more detail on this later, but I don't want to spend too much on it because I still have so much to do today. But you guys can check that these results check out. Like, go home and do the limits yourself. These are what you get. By the way, there are more examples that are in the textbook in section 1.3, so I'll just note those for you. So there's a uniformly charged thin hollow sphere, or cylinder, thin hollow cylinder. So think like a tube rather than a solid rod. That would be in section 1.3, example 1.3.5. This is in the LibreText. And then also there is a segment or there's another example that they do this for the non-uniform charge density on a rod. So in the example that we just did had a uniform charge density, but what happens if it wasn't uniformly charged? Like what if the charge varied with position? This is also done in section 1.3, and it is example 1.3.4, in the LibreText. There's another example in the textbook I've been linking you to. It basically does the disk calculation that we just did, except it does it via a different method. It does it via integration of rings. So that's linked in the lecture notes as well, and I think that you guys might get a kick out of that. So just some general comments about this that I think that you guys might might be helpful when solving these types of problems, finding the electric field for some complicated thing. So generally, the symmetry of a problem dictates the coordinate system that you choose. Like in the case of the disk, it kind of forced us to use cylindrical coordinates. And if you use the right coordinate system, given the symmetries of the problem will get a lot simpler. But it doesn't always mean that the problem is easy. Like don't mistake easier for easy, because these problems can still be tricky. Also, in real life, this whole even odd function trick that we used in both the disk and the line doesn't actually work in most cases. Most cases, the functions that you have to integrate are neither even nor odd, and you just have to do the integrals. And sorry, that just sucks. And usually, again, in real world scenarios, you have to do the integrals for all three components of the electric field, which is going to be hard. Like in general, if you were just given some general charge distribution, some general mixed up non-symmetric thing, you just have to do all three integrals for all three components, because the electric field has three components. Just in the examples that we did, we only had one that was non-zero. That said, for a lot of these real world things, usually they'll have enough symmetry that you can that somebody has handled the geometry before. So you can just like Google the line element or the area element or the volume element, i.e. what DL, DA, or DV are. And then you can just write DQ is whatever it is based off of what you Googled, depending on the coordinate system that is being used. Now, in the lecture notes, there's a reference of coordinate systems that I wrote down, and it's also at the bottom of section 1.3. I'm not going to go over that because it's just there to reference. It goes over Cartesian coordinates, cylindrical coordinates, and spherical coordinates. And we're running low on time anyway, so I'm just going to move on. It's just a quick review. Go check it out. It's in the lecture notes. It's in the LibreText. There's like nothing instructive there. It's just math. So take a look if you need a refresher as to how to find those area and volume elements. We're going to change gears now, and I hope that we're going to get as far as we can, but looks like we still have a lot. We only have 15 minutes left, so we'll go as far as we'll do as much as we can. I want to talk about dipoles. So we briefly talked about dipoles, I think on the first lecture. Yeah, there's only been one other lecture. We briefly talked about dipoles, and I just told you it's when you have two charges of opposite sign and equal magnitude that are separated by whatever means. Maybe there's like a rod connecting them that they can't like attract each other. And the reason why we're interested in studying these is that dipoles are the most common distribution of charge in nature. So think about it. Where are most charges in the universe? Well, they're bound up in atoms, right? Atoms with a positive charge at the center and a negative charge at orbiting it, right? That's a dipole, right? It has an equal. It's a neutral charge. The whole thing is neutral, but it has but the positive and negative charges are separated by some fixed distance. Now, in reality, that distance can change, but for a stable atom, that distance is just whatever it is. And similarly, for like ions and molecules, ion molecules, you have a positively charged atom and a negatively charged atom, and those are fixed. Those are some fixed distance away, depending on the bond length. So as far as like actual charged, real world applications of electrical fields and stuff like that, the dipoles are the most common, like by far the most common arrangement of charges, right? It'll always be positives will be with negatives. The only time this doesn't really happen is like in plasmas, but that doesn't come up very often. So it's super useful to talk about these dipoles because it's a really good model for what we see in nature. And so just as we did this line of charge, and we packaged this idea of an infinite line charge, which now you can just go use that result elsewhere. And we did the same thing for an infinite plane of charge. So now you know the answer for every infinite plane of charge. You don't have to redo the calculation. If we dig a little bit deeper into dipoles so that we can understand them better, then you can just reuse the results that we do that we obtained when we were studying dipoles whenever we need to talk about dipoles in the future. You won't have to redo the calculation. So that's what we're going to do. we're going to talk about dipoles in depth, so then you don't have to do it ever again. I mean, you might have to do it on a homework or test, but like if you want to use the real world results of dipoles, you'll know how to handle dipoles. So we're going to define the electric dipole moment. And it's a vector, and we give it the name P. Not to be confused with momentum, I'm sorry, it just is what it is. So a picture of a dipole might look something like this. You have a negative charge over here, you have a positive charge over here, they're separated by some distance d. And this vector P is the vector that points from the negative charge to the positive charge. There's only so many letters, okay? So the magnitude of this vector P is not just the length. In fact, it's the magnitude of the charge times the length d, where d is the separation. So P is a vector, so it has a direction and it points from negative to positive. So that's all. I've defined the electric dipole moment for you. So an electric dipole is defined as having the same charge on either side. Has to. So if they don't have the same charge on either side, it's not a pure dipole. So the electric dipole moment P is the vector that has magnitude q times the distance between the charges and points in the direction that goes from negative to positive. That's all. That's all the electric dipole moment is. I want to make something clear, though, just as a quick note of caution. The dipole moment is not the electric field. Like, they're both vectors, but they're basically not related to each other. I mean, like, they're related to each other in a sense that you can get one from the other, but they're not the same thing. They don't point in the same direction. Anything. Yes, you do need that Q1 has to be equal to Q2. That's why I use the same variable. That's why this one's negative Q and this one's positive Q. Now we can draw what the electric field looks like for a dipole. So we're bundling up the dipole into just a package. So now we're asking, what's the electric field around this package? This is our dipole. It's just a thing. Just like how a charge, it might just be a big collection of charges in some distribution. An electric dipole is just something that has an electric dipole moment. So what does that look like? Well, we've actually already drawn this. We've drawn the field lines for this. It looks something like this. All we're doing is we are obscuring, we're obscuring what's happening inside the dipole because we're trying to treat it as like a black box that has a property. We're trying to treat it as anything that has the property of a dipole. So that's why we're not worried about what's happening inside. Just as a quick note, though, the dipole moment points in the opposite direction of the electric field between the two charges. Does the dipole disk have a center or separation between two charges? This is not a disk. It's just like it's like a tube. It's just a thing that has this dipole shape to it. It does have some separation. That's given by d, and it might have some size. And yes, they must be opposite signs with the same magnitude. The point is this is just a package. It's a package that has a dipole moment. Don't worry about what's happening inside. It's just something that has that dipole moment P. So this thing is called a dipole. It has two poles, positive and negative. So for the remainder of this lecture, the remaining 10 minutes, and we'll probably have to continue on next Tuesday about this, we're going to consider how external electric fields affect a dipole. And we'll figure out what the electric field is from a dipole. Yeah, you will. Yeah, we probably will. At least Probably not explicitly. Maybe I'll give you some examples to investigate that in homework though. Haven't thought about that. So we already know how external electric fields affect monopoles, right? A monopole is just a regular charge, right? And we know how an electric field outside of it, like an electric field coming from somewhere else, affects that charge. It applies a force, right? So there are charges here. So we should figure out how an electric field, an external electric field, yeah, that's the point. It does affect the dipole as a whole. We want to figure out how the electric field affects a dipole. So let's do that. So let's look at the simplest case, the simplest external field, where we have the dipole in a constant E field. Now, a constant E field means that both the direction and the magnitude of the electric field are the same at every point in space. What that means is it's just always pointing in one direction and it always has the same magnitude. So we depict that with our field lines as just straight lines in a direction. And I'm going to put our dipole somewhere here. And I'm going to zoom in on the dipole so we can get a better picture. So here's our dipole. We have minus Q over here. We have plus Q over here. We have these electric field lines that are just constant and everywhere. And so the question is how does this electric field affect these charges as they are together? Now you have to assume, by the way, that this distance between them is fixed and that they're like glued, that they're like held together by glue or something. So let's consider the forces on the individual charges. Because we know how to do that, right? The force on a charge is just the charge times the electric field. So the force on plus Q is just Q times the electric field, right? And it would be pointing to the right, because that's the direction the electric field is in. So we assume that the distance between a dipole's charge is always constant. Yes, that's required. The force on the negative charge is the charge times the electric field. So it's negative Q times E, and it points to the left because that's the opposite direction of the electric field. Okay, so what is the net force on the dipole then? Well, hopefully you guys see where I'm going with this. Not E, F. The net force is the force on the plus charge plus the force on the minus charge, which is just 0. So there is no net force on a dipole. So if you just put a dipole down in a constant electric field, it'll just sit there, but it'll do something else a little bit. It won't linearly accelerate, right? The acceleration is 0. It'll do something else. So the way we use Q depends on the direction the thing is going. It will rotate. It is like a pendulum, actually. It will waltz. Yeah, so there is torque. So I'm going to draw the picture zoomed in a lot. We have our dipole. We have this distance is D. This distance points in the direction of the electric field, and this angle we'll call theta. So we have a force this way on the positive charge and a force this way on the negative charge. And I'm just going to declare that that center point is the pivot. And I'm going to call positive torque is the torque that rotates clockwise. Okay, so the torque on the positive charge about the pivot point that I've declared, this would be the moment arm, which is d over 2, times the magnitude of the force, times the sine of the angle between them, right? That's how you calculate torque. Scroll up a bit, there we go. And so we can do some simple algebra. This is dQe over 2 times sine of theta. And this is in the clockwise direction, because if the force is applied to the right, that would cause it to rotate that way, right? Similarly, the torque on the negative charge would be the moment arm, still dq, times the sine or times the magnitude of the force, times the sine of the angle, and also that would cause also clockwise rotation. So it's in the same direction. So it's dQe over 2 times sine of theta clockwise. So the end result is that the magnitude of the net torque, it is a vector, so we have to write magnitude, is it's Q times D times E times sine theta, or written another way, it is the magnitude of the dipole, it's Q times D, that is the magnitude of the dipole, times the magnitude of the electric field, times the sine of the angle between them. But that should look awfully familiar. That is the electric dipole moment cross the electric field. And indeed, it works out that the direction agrees with that cross product. And you can check using the right-hand rule that this is the case. So the torque on a dipole in a constant electric field is just the dipole moment crossed with the electric field. That just is the torque, which is amazing. Is the electric field and the torque that's experienced in the dipole. So torque isn't a thing that can be conserved. And the electric field is constant, but conserved would be a weird way to put it. This is very similar, or this is how a type of motor could work, but most motors actually use magnetism. So in fact, you're right, this would happen. So it will oscillate back and forth. And the reason for that is because the torque will change signs as once it crosses the electric field. P is the dipole moment. P is the vector that points from negative to positive and has magnitude Q times D. It's just how we defined it. It is the dipole moment. It's the electric dipole moment vector. Just as a reference for you guys, if you want to see this in a little bit more detail, see example, or not more detail, but a good example. See example 1.4.1, which is in section 1.4 of the LibreText. Now, there's another thing that we can compute, and let's see if I can knock this out in just a minute or so, a few minutes. Yeah, and then we'll get to the, yeah, that's fine. Another thing that we can do is talk about potential energy. So we already know what the force is in a constant electric field. It's 0. We know what the torque is. It's P cross E. What about the potential energy of the system? So, because I mean, there is obviously some force, and it behaves kind of like a pendulum. So pendulums have potential energy because they have gravitational potential energy. So why wouldn't this thing? And indeed, it does. So there is some external work that causes the rotation, right? The thing's kinetic energy is changing because it's going from not rotating to rotating. And so because its kinetic energy is changing, there has to be some external work that's done. So if it's the case that the electric field produces a force or a torque that's conservative, then we'd be able to rewrite it in terms of a potential energy. And it turns out that that's all true. The electrical force is conservative, just like the gravitational force. So we can reframe these things in terms of a potential energy. So we're going to start with energy conservation, that the change in energy of the system, this would be its change in rotational kinetic energy, that's just equal to the work. So that should be equal to the sum of the work on the individual charges, right? Because work just adds. And so we can actually just do this calculation pretty easily, figure out what the work is. Because the force is constant. The force is the electric field times the charge, and those are just the same. And so because the force is constant, we just need to figure out how far does the charge move in the direction of the force. i.e., we can rewrite this as the force on the positive charge times the distance that the positive charge travels in that direction, plus the force on the negative charge times the distance that the negative charge travels in that direction. So here, delta x is the parallel distance traveled. Along the force, so in the direction of the force. So let me just draw a picture so you can see this. So let's start off with the vertical orientation. So in this electric field, which points this way, the torque that it will experience will cause it to rotate to be like this, right? So the distance traveled is this distance here, where, say, this angle is theta. So this distance would be d/2 times cosine of theta. So that's just what our delta x plus q and delta x minus q are going to be. So, and the forces we already figured out, it's just q times e. By the way, I know it's 1:30, I'll be done in a minute. If you have to leave now, though, it's being recorded, so you can catch up. So this is just Q times E times d over 2 cosine theta plus d over 2 cosine theta. They both travel the same distance. They both travel in the direction of the force. So they both get that contribution of d over 2 cosine theta for the distance, and the force is just Q times E. So this is just Q times D times E times cosine of theta. And if you're good with your vector calculus, so delta y wouldn't contribute because that's not in the direction of the force, right? Because remember that the work is really F dot D. And so the force points in the horizontal direction, either this way for the X or for the negative or that way for the positive. So we have to take the dot product of the two. That's why we're only considering the horizontal component. So QD times E times cosine theta, that looks awfully like P dot E. And indeed it is. So because the electrical force is conservative, we have that the work is just the negative change in potential energy. So this tells us that the change in potential energy of a dipole in an electric field is the negative dot product of the electric dipole moment and the electric field. Promise I'm almost done. 2 more sentences. So remember that when we were talking about potential energy initially, if you choose a reference point, you can just define potential energy. So we define, rather than just the change of potential energy, we define that the energy of the dipole is 0 when P is perpendicular to the electric field. That way, the energy of the dipole is just negative P dot E. And so you can check that the potential energy of the dipole, it's at its minimum value when the dipole is aligned with the electric field. That's also where the torque is 0. So it checks out because we expect that things will go towards their minimum potential energy. So when this rotates to be perfectly aligned, that's when the torque is 0. That would also be where its potential energy is minimum. That is the equilibrium point for this rotation. And it'll oscillate back and forth because it'll still have some kinetic energy, and then it'll go back and forth. All right. I know that was a lot.